in number 13, A, B, and C all deal with the same elevator, right? In the situation in A, so we know it's a 1,200 kilogram elevator, okay? It says it's accelerating downward. That means Fg is greater than the tension in the cable, okay? They tell me the acceleration, and I know the mass. What can I calculate with those two? Net force, okay? So the steps are basically the same for all three, okay? So I got F net equals mass times acceleration, so that'll be 1,200 times 1.05. Okay, so that's going to give me, what does that give me for a net force there? Actually, sorry, negative 1.05 because it's going downwards. What does it give me for a number there, guys? Yeah, it's all right. My calculator started up. Okay, 1,260 newtons. And that's negative. So that's down. So my net force is negative 1,260 newtons. This force here is 1,200 times 9.81 because it's the force of gravity, mass times gravity. That should be 11,776 newtons. Come on. Yeah, well, 72 newtons, not 76, 72. Okay. All right, so now I've got these two forces. Now, I know that my net force is the tension plus the force of gravity. And in fact, that step carries through to all three parts of this question as well. Okay, so if I want to find the tension, all I do is subtract gravity over to this side. So I'll have F net minus the force of gravity equals the tension. The mistake people make here is forgetting to make the net force negative in part A because it's downwards. Okay? So what we have is negative 1,260 minus negative 11,772. Okay? They're both down. Right? So when I do that, I should get 1.05 times 10 to the 4 newtons up. It comes out positive, and it's less than this. Okay, it needs to be. It needs to pull up less than gravity, otherwise the elevator isn't going to descend. It's got to have a net force that's downwards. Okay, so all that changes for part B, which I think is the part people were having more trouble with, is that this is now positive, because it's 1.05 meters per second squared up. Okay, so what changes is, now that number's positive. Okay, so I still have the force of gravity downwards, that hasn't changed, but now when I do this, I go 1,260, okay, minus negative 11,772, okay, I get a bigger number. The force up has to be bigger than gravity, otherwise the elevator is not going to accelerate upwards. I have to have a net force up to have an acceleration that is up. Okay? All right. Part C also gives people trouble sometimes because they want to use that number. Is that number useful at all? The velocity, I mean. You'd be surprised how often I catch people with it. If it's moving at a constant velocity, what's the net force? 0. There's no acceleration. Mass times acceleration is net force. If I go mass times 0, I get 0. Okay? There's no net force if it's traveling at a constant velocity. In fact, you might want to add this to your notes, okay? Somewhere in there. Anything about constant velocity, constant speed equals net force 0. Okay? We have to understand, if it's not accelerating, there isn't a net force. Net forces cause accelerations. If the question outright says, moving at a constant velocity, there's no acceleration. Thus, the forces are all balanced. That's why the answer to C is equal to the force of gravity. The force up and the force down have to balance each other. Okay, so make a little more sense when it's explained? Okay, because there's a real tendency for people to plug that in for A. That's not an acceleration, right? It's a velocity. You see the words constant velocity, that question has just gotten a lot easier. Okay, because you already know what the vector sum of all forces is. It's 0. Okay, constant velocity means F net is 0. Okay, and you can really start going from there. Okay, any other ones?
On question 10,
10?
we just couldn't get like the same answer that was in the key there for some reason. I'm not sure what it was. It looked relatively simple.
And it is, but it's an elevator question. If I throw something vertically into the air, this is 15 kilograms here, okay? The initial acceleration is 8.80 meters per second squared up. Okay, I know mass and acceleration. What can I find right now before I do anything else? Net force, okay. Okay, F net is mass times acceleration. Okay, so 15 times 8.8. All right, so the net force is 132 newtons up. Now, might have got a little bit ahead of myself. I drew a box and then I never completed my free body diagram. Okay, so I got 15 kilograms. Okay, this is the applied force. That's what they want me to calculate. What other force is acting? Gravity. That's the force people forget in this question. Okay? As soon as it's thrown in the air and not an actual elevator, for whatever reason, people forget about gravity, which that's way too big. Okay? It should be a little bit smaller. Okay, so we're going to have Fg is m times g to calculate that force. 15 times 9.81. All right, so that force is 147.15 newtons, and it's down. Okay, what's the other way to calculate net force? Sum of all forces. Okay. Do I have 2 out of the 3 of those? Right? I calculated net force right off the bat. It's 132 newtons up. I calculated the force of gravity. It's 147.15 newtons down. That's the force the question wants, and I know 2 out of the 3.
Isn't gravity like a negative variable?
It is, but I still have to say plus here. I'm going to make it negative in the math.
Okay. But when we add it, I'm getting ahead of this. Sorry.
That's okay. Go ahead, Ness.
I'll wait for you to actually do it, then I'll ask.
Okay. So I'm going to subtract the force of gravity over here. So I'm going to have F net minus the force of gravity equals the applied force. This is where the vector sum part comes in, right? Okay, I'm going to have F net, which is 132 up, minus negative 147.15. It's down. That's the vector sum part. Okay? What a lot of people do is they subtract a positive number there, right? Yeah. So when we do that, okay, we should get, we're effectively adding them together. I would have to apply a force that is equal to the force of gravity plus that much in order to make it do that. Okay, so the correct answer there is 279 newtons up. That is the force I would have to exert to do that. Okay, okay? Those were 2 of the ones I thought you would ask about. Any others? How far did we get? Anybody get past like question 11 or 12? Yeah? No? Okay. All right. Well, let's look at a couple other Newton's second law situations, and then we'll keep working on some other problem-solving stuff here. Okay. Let's say I had this situation. Actually, I'll get you to write this down and quickly draw a picture of it. Okay? And then we'll talk about how we would treat a pulley. Pulley questions come up a lot because they're good system questions. So if I did this, I hung 2 masses that weren't equal over a pulley, what would happen? Heavy one falls, lighter one rises, right? Does that mean that there isn't a force of gravity acting on the light one? Not at all. Gravity's obviously still acting on that one. It's hanging there. Okay, so if I let this system go, I'm holding it like this. When I let it go, is that 35 kilogram mass going to accelerate at 9.81 meters per second squared, or is it going to accelerate less? I mean, if I just had a 35 kilogram mass and I dropped it, it would accelerate at 9.81 meters per second squared. But now it's attached over a pulley to another mass. Is that going to affect it? Is it going to slow it down, or just still going to fall at 9.81? You ever tried to lift something with a pulley? Okay. If you let it go and you're like, or it's like really, really heavy, okay, do you go up at 9.81 meters per second squared? You do. Okay. The forces acting in this offset each other, not entirely, because one box is heavier. But we do have this force of gravity and this force of gravity. Okay? And those two forces, even though they're both acting down, because of the pulley, are going to oppose each other. Okay, so this one's going to be 245.25 newtons. $343.35. Okay. What was the key thing about systems? It was one of the rules I had you write down the other day. All parts have the same acceleration. What does that mean I can do with those masses? Well, I can't cancel them, but I can do something with them. Not quite cancel. The forces almost cancel. Can I simplify this diagram? Really what I have here is two forces that are directly opposing each other. Could I just write this? In the end, that's what's happening here, right? I've got 60 kilograms worth of mass being pulled in two different directions. If the parts of the system are to have the same acceleration, I can combine them to figure out what it is. The acceleration of the system is the acceleration of its individual parts. Okay. Can I find the net force on this system? Comes out to 98.1. I think. Could be wrong. But no. Okay, 98.1 newtons. All right. Yeah, go ahead. So now I've got the net force, 98.1 newtons. Now I didn't put a direction on that. Okay. But that is the net force. Okay. Now what do? I want to find the acceleration. Addison, what do we do next? I have the net force, and I want to find the acceleration. What's missing here? Right. Divide both sides of my mass, right? I've got F net, I've got A, right? So I just take my 98.1 newtons, divided by 60 kilograms. Okay, so like that's essentially the acceleration due to gravity on the moon. This would look like it was falling on the moon. It would, the 35 kilogram mass would accelerate downwards. What's the 25 kilogram mass doing? Accelerating upwards. But they have the same acceleration. So instead of like this, like gravity would make it happen, it's going to go like this instead. Okay, a little bit slower. Still going to accelerate until, of course, the 35 or the 25 kilogram mass hits the pulley. Okay, then it stops. But at least for an instant, a couple of seconds, that's what's going to happen. Okay, so I'm going to get 1.6 meters per second squared. Here's the weird thing about this situation. That is the acceleration of the system. I didn't put a vector on a vector quantity. Why? Yes, Virginia, you're right. Speak up. They're moving in different directions. If it asks me about the system, I can only say the magnitude if the parts don't go the same way. In that two-box question you did yesterday with Mr. Zanoni, they were both moving forwards. So the acceleration of the system was forwards, each box was forwards. It didn't matter. Here, the pulley reverses the force. So one mass falls, the other mass rises. That's the acceleration of the system. If it asks me what's the acceleration of the individual boxes, okay, it says, actually there, it says of each object, then I would say for the 25, 1.6 meters per second squared up, 35, 1.6 meters per second squared down. That's how I would ask it. Okay? If I gave you this on a quiz, I'd say again, what's the acceleration of the 35 kilogram mass? Okay, because I would catch some people, instead of dividing by 60, they'd divide by 35, forgetting the system rule. Okay, and you got to realize that that one's descending and the other one's going up. Okay, little things like that, right? They're just little details that we have to visualize when we see a question like this. Okay, so the system rules still apply. I treated the whole system together with the combined mass. Okay. I wasn't looking for any individual forces, so I didn't have to separate the two boxes. Okay, write that one down and give it a try. Okay, so you got two pulleys. Doesn't change a thing. Okay, doesn't matter how many pulleys you got in there. Okay, it's still a system. There's three masses in this one. Okay, so in this question they tell us that we got the two pails. They give us the masses of the two pails, right? So the truck tire is 20 kilograms. Okay, the first pail, pail B is 8 kilograms. Okay, and this one is 6 kilograms. Table is somehow frictionless. Okay, we just say lots of things are frictionless because it's easier. That said, how many forces are acting in this system? 2. Force of gravity on pail B, force of gravity on pail C. Okay? Those are the forces that we have acting here. So we could say, all right, we got this force of gravity here. Okay, it's going to be 8 times 9.81. Okay, 78.48 newtons. Okay, force of gravity on this one, 6 times 9.81. So that should be 58.86 newtons. Okay, going that way. All right. It wants the magnitude of the acceleration of the system, because that's all I can give if I'm giving the acceleration of the system, because tire is going to go to the left, pail B is going to go down, and pail C is going to go up. All right? Yeah, okay, I've got those directions. If it asked about any individual part, I'd be able to give it. But I need the magnitude now. So, can I simplify this system? Okay, combined mass, right? I can just combine all the mass into one thing. So I have 34 kilograms worth of mass. The 20 kilogram tire and the 14 kilogram worth of pails. This way, there is 58.86 newtons worth of pulling force. This way, 78.48 newtons worth of pulling force. All right? So now I should be able to calculate my net force. Okay, I can't use mass times acceleration yet, but I can use the vector sum of all forces. So that'll be 78.48 plus negative 58.86, because it's opposing, it's going the other way. That should give me 19.62 newtons to the left, and for the tire to the left. Okay, so now I've got the net force. Can I calculate the acceleration now? Okay, so 19.62 newtons divided by 34 kilograms worth of mass. Okay, 0.58 meters per second squared, and that's all I can give. That's what they asked for, the magnitude of the system's acceleration. Okay, if the question had asked for the tire, that number left. Okay, pail B, that number down. Pail C, that number up. Okay, everybody all right with that? Have basically all of the problems you've done still come down to those two things. Sum of all forces, m times a. How you get to sum of all forces is always going to be different. Okay? Every question's got some little thing in it that you have to watch for, but it's always those two steps. Okay, that one we don't need to do. All right, write this one down and draw me the diagram for it. Okay, this is what we call a static condition problem. Still a Newton's second law problem, but it's a static problem. What does static mean? Not, or unchanged, yeah, unchanging, not moving, yeah. Okay, so think about that when you're drawing it out. Static means unchanging, not moving. All right, so I have this sign. Its mass is 35 kilograms. It's hanging from two buildings. Okay, and thus it has two cables attached to it. Cable 1 is angled 55 degrees below the horizontal from one wall. All right, I'm just going to draw that wall over here. Okay, and I'm going to draw a cable that is angled below the horizontal attached to the sun. Okay, and I'm going to say that that angle there is 55 degrees below the horizontal. Okay. Cable 2 is horizontal and attached to a different wall. So this is just cable 1. And this is cable 2. What's the tension in cable 2? In other words, how hard is cable 2 pulling? What do I need to remember about this situation? What's the acceleration of this sign? Right. So what's the net force in this question? All the forces in this question are balanced. Right to left, up and down. They're all balanced. Otherwise, the sign would be moving. Sign's not moving. Well, sign would be accelerating. Sign's not moving. That means also not accelerating. That means all the forces acting in this question are balanced. Okay? That's why we call it a static question. It's static, it's not changing. In this case, it's not moving at all. So, obviously we've got two forces here. We've got the force in cable 1 and we've got the force in cable 2. What's the force I haven't drawn on here yet? Anything hanging would be affected by gravity. Okay, so this is going to be 343.35, right? Is that right? Okay, that's the force of gravity, 35 times 9.81. So that force is acting down. So if there's a downward force and there's no net force, there has to be an upward force. Where is it coming from?
tension of the cables,
Yeah, which one?
probably the angled one.
The angled one. Why can't an upward directed force come from cable 2? Cable 2 is horizontal. It can't pull up. It can pull to the right. That's all cable 2 can do. Okay? Because it's horizontal, the only direction cable 2 can pull is that way. This cable, because it's angled 55 degrees below the horizontal, is pulling to the left and up. This is where visualizing a situation, being able to see the forces, starts to get a little crazier, right? You've got to be able to now see invisible forces, okay? The components of some other force that's acting and how they're helping to balance off a situation. So if the sign's not moving, how big is this side of cable 1's triangle? Josh, how big do you think it'll be?
No idea.
I think you do. I think you do have an idea. The sign's not moving, and there's a force of 343.35 acting down. How much force is acting up?
30, 40.
Exactly. Same amount of force. Okay? If it's not going to move, that means the net force has to be 0. That means the force is down and the force is up have to add up to 0. So this force and this force balance each other out. Okay. Is that also true for cable 2 and the left directed part of cable 1? It has to be. The net force was 0. This sign's not moving. That means all the forces have to be balanced. Okay? This is the really intuitive part, okay, of these kinds of questions. The math here isn't going to be that hard. We multiply 35 by 9.81, and we're about to do a trig calculation to get the adjacent side using the opposite side. Okay? What trig function should I use? I have the opposite side, I'm looking for the adjacent side. 10, yeah. Okay, so this side here is the adjacent side. So if I say the tan of 55 equals 343.35 over the adjacent side, all I have to do is move A over there and bring tan of 55 this way. Okay, so basically, the force in cable 2 is 343.35 divided by the tan of 55. Okay, so that side is 240 newtons. We only have 2 significant digits in that question. So, cable 2 has a tension of 2.4 times 10 to the 2 newtons. Does it feel like my answer is missing anything? Well, it never asked me for that. You're right, I don't have the tension in cable 1. You're absolutely right, I haven't calculated that. But it never asked me for that. Does it feel like my answer of 2.4 times 10 to the 2 newtons is missing something? Yeah, it feels like it's missing direction, right? Force is a vector quantity. Well, here's the weird thing about tension. It's about perspective. That's how tight the cable is. From the sign's perspective, that force is 240 newtons to the right. From the wall's perspective, it's 240 newtons to the left. So if you're ever asked for tension, you don't have to give direction. Had the question asked, how hard is the cable pulling on the sign, then you would have to say to the right. Okay? But if it asks for tension, tension is how tight the cable is. Okay? That actually pulls both ways, so you don't have to give a direction when asked for tension. Okay, so even in those elevator questions, we go, what's the tension in the cable? You just have to get a number. You don't even have to say up, unless it specifies pulling on the elevator. Okay? All right, so a question like that, like we drew the diagram, that would be 1 mark. We calculated the force of gravity, that would be 2 marks. We did a trace calculation, 3 marks, and we got an answer. There's not that much work in that question to put on paper. But there's a lot of work that has to go on in your head for it. Okay? That's what's tricky about Newton's second law questions, is how much of it doesn't end up on the paper, or when we get diagramming it, it kind of does. Okay? But how much of it you have to figure out for yourself. Okay? It's why I'll say so many times in this unit, it is not the math that's going to get you. Okay? It's your ability to visualize what's happening. Okay? Guys, here's what I often see. I've been teaching this class for 25 years. Okay? This is where sometimes people who are really good at math struggle. Okay? Because they just want to do the math. But you can't get to the math unless you can see the physics. Okay? That's what makes physics different from math. Okay? Being good at math doesn't guarantee you being good at physics, or vice versa. Okay? So, in this situation, you've got to be able to visualize it. You've got to draw out those forces. You've got to see what isn't seen in a question in terms of what's pulling, which way is it pulling, okay? That kind of thing. All right, make sure you got that one down somewhere. Put a star beside it. That kind of static conditioning questions come up all the time. There's still a Newton's second law question, even though technically they're governed by Newton's first law. All the forces are balanced. Okay, here's another system question, not static. Okay? In this one here, we're looking for the acceleration of the 5 kilogram mass, and there are 32 newtons worth of frictional force between the 4 kilogram mass and the table it's on. Okay, how many forces acting in this one? 2. Okay, there's the force of gravity acting on the 5 kilogram mass, force of friction from the 4 kilogram mass opposing it. Technically, gravity would be acting on the 4 kilogram mass, but because it's not moving vertically, we know that's offset by the table. So, okay, we don't have to worry about, sure, I could draw force of gravity here, but then I would draw a normal force here. Because this box isn't going up or down, those forces don't really matter. Okay? We can put them on there, but they don't really matter in the end. The forces that do matter are the force of friction, which always works against you, okay, and the force of gravity. All right, and for this one, that's going to be 49.05 newtons. Okay, so I've got my 2 forces. Can I simplify this diagram? And I should. Okay. This is what throws people off. In this one, I specifically asked for the 5 kilogram mass. Do I still want to write 9 kilograms in that box? I do. I'm finding the acceleration of the system right now. Okay, so 49.05 there, 32 here. Okay, so that should give me 17.05 as a net force, right? I have 49.05 plus negative 32, okay, 17.05 newtons. Okay, acceleration, F net divided by m, 17.05 over 9. Okay, so the magnitude of the acceleration here is going to be 1.894 meters per second squared. But this question asked about the 5 kilogram mass. So now I need to say it's, well, to one significant digit, 2 meters per second squared down. I have to put a direction on it now. It asked about a specific part of the system. Magnitude is still the same, but I do apply direction in my final answer. Okay, so 2 meters per second squared down, because we only had the one significant digit. right. So as we go along, the situations are going to become more and more complex. Okay? In the end, did we still do the same two things we always do? Okay? That's the key thing to remember. No matter how crazy it gets, you're going to have to find the vector sum of all forces and use m times a. Okay? Maybe not in that order, but those two steps are always going to be there. Okay, see what we remember from yesterday. Okay, the total friction on this whole system is 120 newtons. The friction acting on the 40 kilogram block is 48 newtons. Okay, we want to find the acceleration of the 40 kilogram block and the tension in rope B. The whole system is being pulled forwards with 150 newtons worth of force from rope A. Okay, give you a few minutes on that one, see what we remember from yesterday. So, right now, what's probably the easiest thing for me to calculate? Like, I have the total forward force on this system, and I also have the total backward force on this system. Can I calculate the net force and acceleration of this system pretty much right off the bat? But that's probably what I should do first, because I can't solve for the tension in rope B without the acceleration of the system. Okay, which we'll see in a minute. So what I'm going to do first is simplify this diagram down to 100 kilograms worth of mass being pulled this way by 150 newtons and resisted by 120 newtons. Okay, that's essentially what's going on here in the grand scheme of this system. All right, so what I would do is simply vector sum of all forces, 150 plus negative 120 gives me 30 newtons forward as a net force on this system. That means I can also calculate the acceleration. Acceleration is F net divided by mass. 30 newtons forward divided by 100 kilograms is 0.3 meters per second squared forward. Okay, so that answers what is the acceleration of the 40 kilogram block, because that's the acceleration of the system, and the 40 kilogram block is part of the system. Okay, so it would have the same acceleration. Everybody okay with that? All right, the next part wants me to break the system up and find individual parts. So I'm looking for the tension in cable B. So here's what I have to ask myself. What is cable B pulling on? Okay. Tension, we just said a minute ago, is a force that is kind of point of view related. That means that cable B is pulling forward on the 60 kilogram mass and backward on the 40 kilogram mass. Agreed? Okay, so there's actually two ways for me to go about solving this. The fastest way is to use box A. Okay, to use the 40 kilogram box, sorry. Right? So here's what I want to do. Since I'm having to find a force within the system, I'm going to identify part of the system that force is acting on. Okay? And I'm just going to isolate it. How many forces are acting on the 40 kilogram block? More than two. There's three forces acting on the 40 kilogram block. Okay, there's the obvious one. The 150 newtons pulling it forward. Okay, the question also tells me that there are 48 newtons worth of friction on the 40 kilogram block. Well, friction acts backwards. What else is pulling on that box?
The 60 kilogram
The
box.
60 kilogram box through the rope. Okay, so the other force pulling on the 40 kilogram block is the tension in rope B. Okay, I mean, think about it. If you're pulling something behind you, you can feel the force pulling backwards on you. If you're dragging a wagon, okay, or you've got, you know, some kind of crate and you're just pulling it with a rope, you can feel that. Okay, it resists you. It's not because there's friction there, it's because there's mass there that you're trying to accelerate. So it pulls back. Okay, so that force is pulling back on the 40 kilogram block. If I'd have drawn this with the 60, that would be a forward force, right? But because I know more forces for the 40 kilogram box, I chose to use it. Okay? So what else do I know about the 40 kilogram box?
Maybe something I just calculated. Sophia, what else do I know about it? Right over there.
Right, I know the acceleration. I know the mass and the acceleration. What can I calculate about the 40 kilogram box? Ashley, what can I calculate? The net force. Should I always try to find that? I mean, how many times have I said you always have to do these two steps? I would, if I can, it's always something I'm going to try and find. 40 kilograms times 0.3 meters per second. Okay, so the net force on the 40 kilogram box, I'm just going to write F net 40, is 12 newtons forward. Okay, I'm going to give you a couple more minutes in case you were stuck. Now you know the net force acting on the 40 kilogram block, and you have a free body diagram for the 40 kilogram block. Find the tension in rope B now. Okay, I know what the vector sum of all the forces acting on that 40 kilogram box is. It's 12 newtons forwards. Okay, so can I write this? Can I say that F net on the 40 kilogram block is 150 newtons forward, the tension in that first rope, okay, plus the force of friction, that's 48 newtons, plus the force tension in rope B. Those are the three forces acting on the 40 kilogram block. Okay? I know what they add up to, and I know 2 out of the 3 forces. Okay, so, or sorry, 3 out of the 4 forces, sorry. Okay, so I'm going to isolate the one I don't have. So I'm going to subtract and subtract. So what I'm going to have is F net on the 40 kilogram block minus 150, which is a positive number, minus the force of friction, which is going to be a negative number, equals the tension in the second rope. So positive 12 minus positive 150 minus negative 48. Okay, because the friction was negative. So 12 minus 150 minus negative 48. Okay, so the force, the tension in that second cable or rope is 90 newtons backwards. Okay? Did I end up doing anything different? I still did vector sum of all forces and m times a. Getting there is trickier, for sure. But I still did the same 2 things. Now, could I have solved this using the other block? I could. Okay? It involves one extra step. It's not hard, but it involves an extra step. Okay? the 60 kilogram block, they don't tell me directly how much friction is pulling on the 60 kilogram block. There has to be because there's friction on this one, okay? But I know the total friction and I know how much of it is on the first block. Could I figure out how much is on the second block? I could. And then from there, everything else is the same. I'll just have a 60 kilogram block. I'll have the force tension in B as a forward force, and what would we have there? 72 newtons worth of force, friction force backwards. That is vector sum of all forces. Okay, so you'd have, you'd take your acceleration. The acceleration here was still 0.3. Multiply that by 60. Then you'd have F net. F net would be force and tension B plus the force of friction. And after that, it's the same as what we did before. Okay, you just have that extra step of calculating the friction on the second box. After that, it's sum of all forces and M times A. All right. Questions there? Okay. They get a little hairy. Okay. And we haven't gone into any like super duper vector ones yet, okay, with the trigonometry, right? All right, let's finish off with this one. Also a static condition question. So there's a 120 kilogram, like let's say this is like at McMahon Stadium, they have the big speaker that hangs down from the, or the Jumbotron or whatever, hangs down from the cables. Okay, so it's 120 kilograms, okay, hanging by cables. There's 100 degrees between these two cables. Okay, they're equally long, okay, all that kind of stuff, okay, and they're supporting the 120 kilograms worth of mass. I want the tension in cable A. Spoiler alert, it's the same as B, but okay. Give that one a try. What does that mean the net force is? 0. So that means the forces up and the forces down are equal. All right, so I can calculate the force of gravity acting downwards by just going 120 times 9.81. Okay, so 120 times 9.81 is going to give me 1177.2 newtons. Now, here's what needs to happen here. That force is split equally between the two cables. So each cable has a vertical component that is 1/2 of that. That's the mistake people make here. If I'm going to have a net force of 0, the forces, plural, upwards, have to equal that force downwards. If you make both of these 1177.2, you have a net force of 1177.2 newtons up. That thing is getting thrown into the air massively. Okay, so what we have to do is divide that by 2, and that is the upward force, okay, on each cable. So 588.6 newtons, right there. This angle will be 50 degrees, and then it's just a trig calculation. Right, I'm looking for the hypotenuse. I have the adjacent side, so I simply go 588.6 divided by the cos of 50, and I've got my tension in the other cable. All right, so each cable will have 916 newtons worth of tension force in it. Okay, is that very similar to the other static question we did? Okay. It just has that one extra little thing that catches people, and that is that 1177.2 is got to be split between the two cables. Okay, just little things, but that's why we spend so much time on this, so you get exposed to as many of those situations as humanly possible. All right, I had a bunch of people ask me if there was a quiz tomorrow. There is not. Tomorrow is Thursday. This is our Friday. Okay, so you don't have a quiz this week, but next week, oh yeah, there's one next week. It's going to be all Newton's second law stuff, because that's all we're going to work on next week too. Okay, so tomorrow, more Newton's second law stuff. Hopefully we'll get to a lab early next week.